continuing our discussion of diastereomers and enantiomers. We got a new question here. This is the test version. We're supposed to draw all possible isomers of this name and then label each stereocenter as RS. It's pretty much the same as our activity we just did. And then we're going to label the pairs. There should be either 6 pairs or 3 pairs. We had 6 pairs in our first example. So, before I move too much further, I am going to construct a simple toy right here with 2 stereocenters and okay, here's my toy. Maybe I'll stop sharing the screen. Stop share. So here I am. This molecule has 2 stereocenters. Each stereocenter has a purple group. Stereocenter number 1, stereocenter number 2. They each have a purple group, a green group, and a red group. So you'd think maybe I'd be drawing 4 isomers of this total. This one, it's an enantiomer, and then a diastereomer, and it's an enantiomer. This is what we did last activity. And then the other 4 comparisons were all diastereomers. But I'd like to point out that the mirror image of this specific example is this specific example, because there's something special going on with this toy here. It's got its own mirror image inside the toy. On one side of my hand, which is the mirror, I see purple, and the same distance from the mirror is purple. You see that? Same for the red out in front, same distance from the mirror. And the green in the back, I'm rotating to the top, same story. This molecule is identical to its mirror image because of this. What's the mirror image of this? If I put a mirror here, it's this. Is that a new molecule when I do that? I take the molecule and I rotate it there, and it's exactly the same as what I had there across the mirror, but they're not, I mean, they're not mirror images. Like these 2 are mirror images, but they're different molecules. Look, they don't match. If I'm doing this and then this, you're not going to tell me those are different molecules ever. Okay? I just took the exact same molecule and rotated it right in front of your face. And you can't say it's a different molecule. I didn't break any bonds and go from here to here, did I? No. Okay. But I can't say the same for, this and this. Okay? They don't match up. I wanted to save time by not making the mirror image of this. Do I have to make the mirror image just to show you that all the parts will be exactly the same as this? I don't think so. So this is a special molecule. It's got more than 1 stereocenter. That's criteria number 1. And it's got an internal mirror plane. Okay, we couldn't say that for our previous example. Share screen. Previous example was found, I believe, here, Starboard Software. Where's the answer to my previous one? Oh, there we go. Got it. These are definitely mirror images of each other, and they don't have an internal mirror plane. If you tried to see if there's a mirror plane, here's what you would do. You'd cut it in half, or cut it in half here, and that's not even half. Right away I know it's not got an in plane, a plane, because this group here is a 1, 2, 3, 4 carbon group. This is only 1, 2, 3. They don't match. Okay, I go to my new example, which is this one. And I'm going to draw one of the molecules right here. It's got a bromomethyl here and a bromomethyl here. And it's got an isobutyl here and isobutyl here. Could have drawn that a little better. Yeah, I had a boron there by mistake. Bromo underneath, isobutyl on top. Can I just draw it a little nicer? Sorry. I want it to look the part better. And we got this. And if you do the 1, 2, 3, 4 thing, 1, interesting, 2, 3, 4. And I'm going to connect the 4 on a dash. This one I wasn't forced to draw a particular isomer, was I? So you notice I made an executive decision to put the 4 on a dash. You can do that on the other side of the molecule too. I'm gonna make that the wedge. Oops, they gotta be adjacent. Make this the wedge. This the dash. And that goes 4, 3, 1, 2. 2s are the same. And that is definitely R, and the blue is definitely, that goes 1, 2, 3, and the blue goes 1, 2, 3 is F. Make it blue though. Okay, this molecule has that thing I was talking about. Shouldn't have put all the work on there. It's got the plane in the middle. I will try to show right there. This is called the mesoplane. That's a little big. Mesoplane. You see that the CH2 here matches the CH2 across the mesoplane. This C is identical to this C across the mesoplane. This C got cut in half. You can cut a carbon right in half, and it's half a ball. C is half a ball, right? The CH2Br, same distance from the mirror. Yeah. Because there's a mesoplane, this molecule does not have an enantiomer. There is a mesoplane. The molecule does not have an enantiomer. So I'm going to outline the steps from the previous page, A, B, C, D on the previous page. And it's always those 4 steps. Except when you have a meso, you get rid of one of the molecules because it doesn't exist. This molecule is the same as if I drew the mirror image. Please don't draw the mirror image. So I'm going to leave this one blank here. And this was B from activity 1. This was like A from activity 1. Except you made the stereo centers. You weren't forced to have one of them R or the other S, so you just made them, and you made them the easiest way possible. We have a question. Yes. Sorry? Isobutyl, did I not copy isobutyl? It didn't get copied properly, yeah. Yeah, I copy pasted, but I forgot to grab everything. Thank you for seeing that. There. Yeah, now it's, yeah, it wasn't mesoplane until I fixed that, was it? Yeah, because those groups were not identical when I made the mistake. Okay, so from activity 1, leave blank. This thing doesn't have an enantiomer. From activity 1, I had a strategy for the third molecule. Want to go look? Copy your first molecule, except do a single switch on one of the stereo centers. Good job. It's a good strategy. I'm going to copy everything, and I'm going to switch the isobutyl with the bromomethyl. Here it comes. And here's the bromomethyl on the wedge. And here's the isobutyl where the bromomethyl used to be. Make sure you copy the other stereo center exactly. And now we have a RR molecule, R. How do you know that one's R? It was S, and I did a single switch. That is a strategy to give the opposite stereo center. And the other strategy was drawing mirror images, which we're going to do next. Ladies and gentlemen, I changed the stereo center, but I didn't do any change. What? That's not S. Isn't it identical to the one previous? That was the reason I have this strategy. It's R. Dangerous to talk and write at the same time, obviously. Okay, and guess what the mirror image is going to be in terms of R's and S's? What's it going to be? What's the mirror image of R? S. So I'm going to have two mirror images of R's, two S's. So you put your mirror down, mirror, mirror. Same distance from the mirror. And that's going a little away from the mirror, down a little, and that comes back a little further than the other dash. And what do we got over there? We got mirror image of a purple R is a purple S. I got a tip I'm going to write for the bottom of the screen. Mesomolecules have as many R's as they do S's. Does that make sense? What's that yellow thing? A pink thing, sorry, in the middle of my mesomolecule? Mesoplane means it's you're going to see a mirror image of one side of the molecule on the other. What's the mirror image of an R? S. So here's my mesomolecule. I didn't copy the stereo center. It was R. So hey, they better have as many R's as S's, because across the mirror an S is an R, right? So the statement doesn't need to be said, but it's a good tip. Because sometimes it's not so nice. When the molecule's not in a ring, sometimes you can't tell if it's meso. So that'll be our next activity. Meso or not meso? And we'll do that on a separate sheet of paper. You know, but we haven't finished this question. We're close. We are close. Going to do our comparisons. So if you got a plane in the middle of the molecule, it will not have a mirror image. But the other comparisons are still there. I don't know. Don't do this one enough. Got to compare those two. And then got to compare these two. Now we got to compare these two. Why don't we do the bottom one first? What's the relationship when both stereocenters are opposite? Enantiomers or diastereomers? E. What do you call it when one stereocenter, in this case, the blue is the same, but the purple is different? D. And these two, the purple stayed the same and the blues are different. D. Okay. Well, 12 points this time instead of 18. You get 2 points per molecule, so we lost 2 there, and you'll have 3 less comparisons. That's 3 more. Doesn't seem like it adds up, but that's okay. And there we go.